Hello and welcome everyone. My name is Eric Franzen, President of SemanticWeb.com. First off, we would like to thank you for joining us today for this webinar, a joint production between Dataversity and SemanticWeb.com. Our primary speaker today will be Conor Dowling, the CTO of Caregraf. Today, Conor is going to be discussing the ideal medium for health data, a dive into lab tests. We are also pleased to have with us David Booth today. But just a couple of things to get us started. Due to the large number of people that attend these sessions, you will be muted during the webinar. For questions, we will be collecting them via the Q&A section in the bottom right-hand corner of your screen. Or if you like to tweet, we encourage you to share highlights or questions via Twitter using #SemanticWeb. As always, we will send a follow-up email within 2 business days containing links to the slides, the recording of this session, and additional information that may be requested throughout the webinar. Also, just quickly, a little bit about our speaker today. Conor Dowling is the CTO of Caregraf, which uses semantic web technologies to help healthcare providers gather and analyze the information they create during the course of a patient's care. He's a specialist in clinical data analytics with a focus on how the definition of clinical know-how and institutions shapes the description of patient care. Now, to get us started on today's main content, please allow me to introduce David Booth. You may have heard David in part 1 of this series on the Yosemite Project. David has been one of the primary organizers of the Yosemite Project, and he's going to help put today's webinar into the larger context of the Yosemite Project. Hi, David.
Hi, Eric. Thank you. Eric, if you could switch to the roadmap slide, that would be good. So the Yosemite Project articulates a roadmap for achieving semantic interoperability of structured healthcare information, and it uses RDF as a semantic foundation. Today's webinar by Conor Dowling describes some of the work that addresses Step 2 of the Yosemite Project roadmap. Step 2 is to define RDF mappings to and from native data representations of common healthcare information representations, and Conor's work has mapped the native data representations of the VA's electronic medical record system into RDF in order to make VA healthcare data interoperably available as RDF. So, Conor, thank you very much for joining us today.
Hey, that was short and sweet, David. Thank you.
Yep.
I suppose it goes over to me, does it? And I'll
just
do a full screen. Yeah. Let me do an enter full screen. Where? Oh, hold on. Let me stop that. I think I have to manually say I'm sharing, right?
Yes, we're just.
Oh, I'm now the presenter.
A formal presenter.
So you should see my screen right now.
Not yet.
Oh, okay. I actually have to share it. I think I share an application. Here we go. I'm sharing Safari, and then I'm going to enter full screen. So you should see.
Perfect. Yes.
You see the full screen?
Full screen. If you could stretch it out a bit, make it full screen. We should.
Yeah, I did enter full screen. Let's see if it works a second time. Second time's a charm. Okay, there we go. So, thanks for that, David and Eric. I'm going to go, when we first did these presentations, they were a little bit shorter. And what I presented at that stage almost solely focused on lab data because there wasn't enough time to consider lots of different domains. So I'm going to speak a little bit more broadly than lab data, but to the lab data examples I did when we first, in the last meeting of the Yosemite Project, was presenting this sort of thing. And just to begin, I'd like to step back and just consider a very general question, which is we're saying you should use RDF for health data representation in general, and specifically for a medical knowledge representation. And it seems easy, that seems an obvious thing if you know all about RDF or you've already bought into the tool chain, or frankly, that's just how you make your money, you're going to promulgate that particular message. But I think if RDF is going to be adopted in this area, we have to actually show that it brings a new scale. It brings new techniques and methodologies that greatly enhances both the way we represent clinical data and represent the medical knowledge that underlies it. Now, if you look at the screen right down at the bottom, there's an old quote from Marshall McLuhan. And most people have heard the cliche, the medium is the message, but they mightn't know exactly where it comes from. And if you read that quote, it's basically saying the medium is the message, the personal and social consequences of any medium result from the new scale that's introduced into our affairs. And in a nutshell, what that's saying is that the medium you choose for your content emphasizes certain aspects of the content. And when McEwen was writing, he was talking about media as people, TV, radio, today the web. So for instance, if you put a piece of information on the web, you're immediately reminded that it connects to lots of other pieces of information. If you listen to the same content on the radio, you'll hear these sonorous voices, you may hear some emotion. You can often get absorbed into the story itself, but you're not particularly thinking about clicking on lots of other things that are related to that story. If that same content is on a TV screen, the visual dominates. Often context is dropped and people, there's a lot of sensationalism on TV as a result. And that's all that the medium as a message basically means. And what we contend is that RDF as a medium, the unique qualities of RDF, when it's applied to healthcare data, introduces certain emphases that we believe will move health representation to the next level. Now, if you look at the diagram in the middle of this screen, on the left-hand side you see that, look, we're not starting with a green field. So this isn't a case of us coming in and saying, let's suddenly start defining lots of medical knowledge because it was all so well defined before. We actually deal in a world where, literally back to Hippocrates, they've been defining in taxonomies and lexicons for medical knowledge. And since the 1950s, they've been making those things computable. And today we deal with schemes that come from different owners. They came from different eras, but they're still around. For example, Mesh's PubMed started largely in the late 50s. And they actually come in different media. And those media emphasize certain things and de-emphasize other things. And we think RDF can tackle a lot of that. So if you wanted to assemble medical knowledge available underneath a clinical data record today, you'd have to gather it from various places. So for example, SNOMED, which is being pushed certainly for a lot of disorders and problem lists, although it does a lot more. That comes in a format called RF2. It's their own format that handles version control and other things. RxNorm comes in RRF, which is the format of UMLS that was defined by the National Library of Medicine. The ICDs come in comma delimited files. Unicodes from the FDA come in their own comma delimited files. The NCI tried a version of their big thesaurus in OWL, but it's also available in other formats. The self-reported drug data from all the drug companies when they give information about drugs, and that then leads to those labels you get when you fulfill a prescription and you see those inserts that come in the box with your prescription. Those structured product labels, SPLs, come in XML. It's the particular flavor of XML that's also used for CCDs, for patient care, and has the same downsides. It tends to emphasize syntax rather than semantic correctness. You tend to be obsessed about getting the tag layout right as opposed to getting the content just right, and often whole sections of content are actually missing or can even be inconsistent because there's no semantic check, there's only a schematron syntax check. Now, to look at RDF in the context of what's already there, this pre-existing gaggle of things, we have to take all these things and put them into a graph. And we want a consistent representation across all of them. There are different ways you can RDF things. The bioportal, for instance, basically takes things in different flavors of RDF. What I'm going to talk to today is putting it into a particular flavor of RDF inspired by SCOS, which is a knowledge representation standard from W3C. And the second thing is it's a style of RDF where you it's a DAG, it's a directed graph. You don't have bidirectional links between concepts. I don't know if I'll have time to bring that out, but that's an important part of doing graph analysis on all of this knowledge. And once you get all that stuff in there, we can now start examining, well, is RDF new? Does it introduce a new scale, a new sense of power? Just before I get off this, let me quickly just go to the server that's behind all the different anecdotes and stories and examples I'm going to show you. What we're actually doing, all of that information, as you just saw, is put into a basic triple store. That triple store, in front of it, there's a search engine as well as the triple store, so you can actually search things lexically, because in medicine that's often a very common thing to do. If we go to, for example, one of the VA's definitions of warfarin, all of that information is within the triple store. This browser client pulls that information out, and you can see all the various pieces of data, all the various relationships as far as this VA scheme is concerned for warfarin sodium. You can do exactly the same thing for SNOMED. And for instance, if we go in, we can find that this concept in the VA is exactly the same as this concept in ORIX norm. And we can also actually go to a query interface that will actually let us directly query using Sparkle. If you know a lot about triple stores and Sparkle, you can directly use Sparkle against all of those schemes as well. So that triple of a search engine, a rambler around a consistent representation in RDF of this gaggle of schemes, and a Sparkle endpoint that lets us write arbitrary queries is what's behind what I'm going to show you. And let me get rid of that. I'm not really going to click much more on that. One of the things, just to get at one particular message for ODF. Here's an example of assembling in such a triple store enough of these schemes that we're going to get 1 million concepts. We're going to get 1 million disorders and drugs and lab tests and other things. We just want to get just over the 1 million. And you see the various schemes on the left. They all, as I said, come in different forms. We've put it into this one RDF form. So you have the different ICDs, you have NDCs, which are inside SPLs. That's how the FDA labels drugs. It doesn't just designate the drug by its chemical ingredients and its form. It also knows the labeler or packager of the drug. You have NDDF, which is First Data Bank. That's often used commercially for designating drugs, as opposed to some of the more standard open ways. ORIX norms, the NIH's drug scheme, SNOMED we talked about, and you can see the relative proportions between things. So you look at that and you go, that's a lot of concepts. And that's not even all of the concepts that you deal with. I haven't got LOINC in there, you notice, which is the lab scheme. But it's still a hell of a lot of concepts we're dealing with. But when you actually step in a little bit further and you start looking at the different concepts by the category they belong to, we start seeing that there's an enormous amount of overlap between all of these schemes. So for instance, there are literally 12 different ways in which substances are defined. The same substance, it's just given a different concept identifier in these different schemes. There are 10 different ways for drugs. If you look at drugs here, here's the VA's, one of the VA schemes for drugs, the NDFRT, the 16,819. Here's the other VA designation for drugs, the VA NDF, completely different identification scheme. The VA likes drugs so much it names them twice. It's kind of the New York of drug schemes. The NDDF from First Data Bank, again, similar kind of numbers, slightly larger. SNOMED defines drugs, same drugs, just different identifiers. ORIX norm does it too, obviously. By the way, the numbers here, in case you're wondering, one thing about presentations like this is folks will go, well, hold on, where are those numbers coming from? Are they current? How current are they? Literally, this widget here is riding on a file that had numbers from late July, because we gave the first version of this presentation in early August. If I actually click on this, it's live. I can go back to the live server. I actually find the current number is 17,094. But nothing I'm going to say and show you today, even though the numbers are from late July, are no longer true now because we're in early November. And that number here was last updated literally on the 3rd of November. That's the last version. That's the latest release of the VA file, so we can actually see that. So what we've got here, it would appear, is not really 1 million concepts. It's far less, with lots of repetition between these different schemes. And what RDF lets us do very quickly is interlink these equivalent concepts so that we can then go a step further and actually reduce down the number of concepts that we have to a manageable set where we're only actually representing each type of concept once. Now, there's a number of ways to do that, and I'll talk about the way RDF pushes you, which is, I think, superior to the way UMLS and some of the other stuff has been done down through the years. So let's just take a very simple thing. We were talking, if you look here, here's substances. You see substances defined by the VA, substances again defined by the VA, substances defined by First Data Bank. Another variation by First Data Bank where you collect them into sets. SNOMED substances, and then a huge big balloon, which is Unicodes. And I'm just highlighting that because Unicodes is the substance definition scheme used by the FDA. It underlines all of the drug submissions by drug companies, as well as lots of other things, allergens and other things. So it's very, very comprehensive. And it effectively is a superset of the designations in all these other schemes, which really explains, I hope, this diagram here. So here you have in the middle the Unicode or concept for warfarin, the blood thinner. And you have all these other designations around the edges of all these other schemes designations for warfarin. This, by the way, is LOINC. This is the lab scheme. If you represent warfarin in blood, this is how LOINC designates warfarin. It doesn't use a uni-concept code, although it could, and we'll talk about that in a second. NDDF has its own Oryx norm, SNOMED. These are major schemes that are out there, either commercially used or being promulgated and pushed for standard use in health records. And they all are basically labeling again and again and again. It's like you have 10 different Adams in the garden naming all the flowers and fruits rather than just one. And on the left-hand side, you see the VA actually has 3 different designations for warfarin. It has one in its VUID scheme. It has 2 in its NDFRT, one of which it copied from MESH, which is how you index PubMed. MESH is maintained by the National Library of Medicine. They also maintain Oryx norm. So they are actually maintaining 2 different designations for warfarin. And then down below, you have 2 schemes that take a different approach to this variety than we would suggest, and that RDF as a medium promulgates. One is UMLS and one is the HDD from 3M. And what happened was they recognized, quite rightly, that we have all of this overlap between various schemes. How do we solve that? Well, what we're going to make is a scheme of schemes. We're effectively going to make up an identifier that we will then map all the other identifiers into. 3M did that, so did the National Library of Medicine with UMLS. And then all these different things are meant to point into their scheme of schemes. The problem there is, well, now you've got yet another identifier. How do you keep it up to date to make sure you're covering all of the things that come out from all these guys? And on top of which, well, who gets to name the scheme of schemes? Is it 3M who do it commercially, or is it UMLS? Which is the scheme of schemes you're going to use in your health record? Or do you use one of these things? And in RDF, because of the way it's structured around URIs and namespaces, you're encouraged not to go and make up a new identifier. You're instead encouraged to start reusing existing things, to mix and match identified things even though they come from different schemes. In RDF, you would say, I'm not going to make up a scheme of schemes. Instead, I'm going to pick the best, the scheme that has the widest coverage for substances. I'm going to make that my master scheme. Everything else I'm going to reduce to that particular scheme. Now, how that works is if you put the warfarin oral tablet definition from Oryx norm into the triple store, you will see that it has a relationship to the dose form in Oryx norm and to the ingredient in Oryx norm, which I've actually crossed out. Because what we've done in the triple store is we run a graph algorithm and we basically mix these intermediate links that go between this designation for warfarin and the one we're now picking as the master, the uni definition. And now we're actually defining Oryx norm in terms of Unicodes for substances. And we've gotten rid of a whole bunch of substance concept identifiers in our unified graph that was designated just for the Oryx norm scheme. Now that seems to make sense. I mean, why should everybody be making up all their own schema IDs? And now we get to medium again. The main reason for this is if you're editing Oryx norm in NIH, or if you're editing SNOMED with its toolchain, you can't pick a substance ID that isn't defined within the scheme itself. The tool chains themselves, the mediums they've chosen to define their schemes, don't allow for reuse of concepts. They allow for mapping out, but they don't allow for reuse. And what RDF says is, I don't care. You can take your substances from uni, you can take your disorders from SNOMED, you can take your normalized drugs from Oryx norm, you can take your packaged drugs from NDC, and it can all exist in one graph because of namespacing. And you see the namespacing here. It's clearly this is in the uni namespace. Clearly, this is in the Oryx norm namespace. There's no problem combining them. Now, this seems really simple. I mean, if you're in software, this seems trivial. However, think about what's been going on for years, all of this overlapping definition, and then these meetings where people get together and claim they're going to do mapping lists between each other, when in fact in the first place, if they namespace their stuff and actually reuse the best of what's out there, there will be no mapping issue at all. Now let me get on to something that's specific to labs. And by the way, this talk hopefully gets lighter as we go along. That's about as in-depth as I get. So I did say I talked more to labs, and we did talk a lot more about that in early August. This representation of lots of concepts in one space, namespaced, is not just for standard stuff or for commercially available licensed stuff. Probably other than billing software, the most interrupt data today isn't actually e-prescribe, although that's coming up very fast. It's actually lab data. Most large hospitals outsource a lot of their lab tests, and a lot of that is automated. So they can order those tests from Quest and other large lab data providers, lab test providers, I should say. And to do that, they've got to designate those tests to Quest. Now it happens that every Quest lab has its own designators for tests. So different Quest labs have their own designators for tests. Internally, most hospitals have their own designators for tests. And what you see here is a concrete example. This is actually the Department of Defense. When a doctor orders a test, I'm going to see what this is for in a minute. When a doctor orders a test, for, now let's see what it is. It's H. pylori in stool. So this is probably the only presentation today that you're going to actually have somebody talk about H. pylori in stool. The doctor uses the national DOD standard. You may not know this. He uses the national DOD identifier for that lab test, not a LOINC code. And that national standard can exist in the same namespace in the same graph as the LOINC codes because it has a namespace in ODF. Inside the router, the routing software, CHCS is the name of the system that does this. It has a local designation of the test, it understands the standard test, and it also has the Quest IDs for that test. There's a different order ID from the result ID. And it can send that to Quest, and it can get back from Quest the result ID. Quest also very nicely and kindly sends back the LOINC code for H. pylori in stool. So at least you have a standard designation there. Although in this case, actually the DOD ignore it. They go on using their own designation. In addition, there's a CPT code, a billing code for this class of test that's also a standard thing. Every one of these things, because of URLs and namespacing, can be mixed into the graph that I talked about before. And equally, we can reduce them down, as I talked about reducing down the OREX norm substances. There's no difference between local schemes for labs, which are probably the biggest local list there is, and standard and national and commercial schemes. They're all just namespace things that we can mix and match in order to come up with the representation we need to exchange clinical data. Now that talks, what I've now talked about is one thing about the ORDF medium, in emphasizing links, URLs, URIs, namespaces, the ability to mix and match, the ability to easily reduce, the ability to get away from constantly everybody coming up with their own identifiers. That's one big thing with the medium. Here's another one. So here's a lab test, LOINC. You have, this is how it looks in ORDF. I showed you a bit of that at the start. And the glucose test is ranked number 4. When they came up with LOINC, they basically said, look, how many dimensions will we need? How many slots in our medium do we need to represent tests? And what they came up with was the magic number 6. They actually, if you read the various specs, it seemed to go from 3 to 4 and eventually to 6. And in fact, in this particular case, for this simple test, they only really use 5. The method, the lab is meant to normalize the method they use for this test to a standard or common range of values. And so you never have to specify your method. It's that generic. What component is measured? This is a count that's measured. The scale type is quantitative. The component of what? In this case, it's serum or plasma in blood, and it's at a particular point in time. So that's what they've designated there. And obviously in ORDF, you are going to represent that as a particular component. You can also put in extra annotations like example units and other things that you don't need in the definition that just help you understand it better. But all this data here can be represented in ORDF. We come up with link types and predicates to represent it. But look at the thing on the right. Now, it's not as popular a test. It's called a challenge test. So this is where you were told to fast before they were going to do a blood test on you. You know, you had to fast overnight, you come in the next morning. Or in this particular case, you ate 1 hour before the test, and you took the glucose orally. PO is Latin for orally. So basically what this is saying is, it's very specific. It's saying that not only is this a test on your glucose levels, but your glucose levels after you drank a certain amount, 1 hour orally before the blood sample was taken. So it's a very precise designation. Now your 6 dimensions break down. Your comma delimited, all those different columns break down. Where are you going to stuff this extra information? Well, cleverly enough, they overloaded component, and they started splitting it with little hats and various concepts that would mean that you can add in and effectively coordinate in various extra stuff. RDF isn't afraid of predicates. So we can break down this component. We keep the substance glucose separate, because after all, we've talked about doing substances in Unicodes. And we break up all these different things into separate predicates. And even if Lloyd comes up with, or there are various lab tests with all sorts of added dimensions, optional dimensions, optionality is not something RDF worries about, we can capture it within the graph. And we capture it cleanly, not with what are effectively hacks, to make sure that we can still fit into that fixed set of dimensions. That is one more advantage of this particular medium. We're not afraid of extra dimensions, even if they're optional, and we can then properly capture all of the nuance available to us. Okay, let's jump up to Siegfried and Roy, or I should say Aeschylus and Roy. So the Greek playwright, I think he died in Sicily, Aeschylus, was famously killed by an eagle dropping a tortoise on his head. So he was actually struck by a turtle. And if you were to designate how he died, or presumably injured first and then died, you would say that he was struck by a turtle. Now ICD-10, which is going into operation right now, is actually quite good about turtle strikes. So if you are attacked by a rabid turtle, ICD-10 is your man. You can designate that disorder very precisely in ICD-10. In fact, you can say you were bitten by it, struck by it, or in some other way affected by it, and they are all different designations. In fact, and this really threw me the first time, not being a classification specialist, I thought, man, they've even got an ability to say the strike was initial or subsequent. So you can imagine to yourself that the turtle strikes you once and then hunts you down and strikes you again. That's actually not what that means. It means that you have an initial visit due to the first strike and a subsequent visit afterwards, a follow-on visit, and that's what that's codifying there. So sometimes the lexical labels aren't exactly intuitive. You actually have to know something underneath them. But look at SNOMED. In SNOMED, you can only say you were bitten. So in SNOMED, you literally, right now, in a pre-coordinated way, you can post-coordinate it, but in a pre-coordinated way, built in, baked into SNOMED, there is no concept designator for the fact that you were struck by that turtle. So we cannot describe what happened to Aeschylus. To describe it, we will go to ICD-10. And here's an example where I said we could use Unicodes for all the substances, or maybe SNOMED for the disorders, and we start effectively taking the best bits from each scheme. We also have to recognize that that may not be a clean divide. There may be things in one scheme that are not in others, and we may take one scheme as a priority and then the best of other schemes. And again, that's something we can mix and match very readily. Now to show you, I mean, what's best, what's not, it's not that SNOMED is any kind of a duffer. Roy Horn was bitten by his beloved white tiger during a magic show, a 7-year-old male, so 2003 he was bitten. To capture that, now you go to SNOMED. You can actually in SNOMED capture the fact you were bitten by or attacked by large mammals, lions, tigers, hippos, monkeys. It's extremely good at being attacked by these larger mammals, usually African mammals. So if you're attacked in Africa or in a magic show in Las Vegas, SNOMED has great coverage. ICD-10, on the other hand, rubbish. You can basically say you were bitten by other mammals. It's very good at things to do with the sea, dolphins, gators, sea lions. I presume that's something to do with the fact that there's a lot of these things happen in Florida. Lots of things happen in Florida that aren't too good, let's face it. So ICD-10 is good at that. And this, I know this seems very trite, but here is an example of coverage that largely reflects perhaps the emphases and the priorities of the people defining things because of where they're at. Certainly we have to cover things in Florida. We looked at the common disorders in the United States. It's very rare to be bitten by a white tiger. But if SNOMED is covering Africa as well, that's maybe not as rare. So Asia or Africa, it's not as rare, although I'm sure it's still pretty rare. And this, in the RDF sense, we would mix and match. We'd probably take SNOMED for disorders and then still have various things, or at least call out those things that are already coordinated in SNOMED that are actually coordinated in ICD-10. Now let's get on to something. Let's step back a little bit and then we'll go into the extent of definition and how RDF makes that balance up. So what we want in medical knowledge representation is to try to see what parts of medicine are very well understood and where, frankly, you have designations where either we understand what's going on, we understand maybe even why it's going on, but we have no cure for it, and other situations where we can actually tackle a problem, but we have no idea why it arises. And that's what this graph, this is Clayton Christensen's graph. You may disagree with the placement of certain of the boxes, but what it gets to is that stuff I just talked to. If you look at the x-axis, it's talking about the extent to which we understand something. So can we, for example, a fracture, strep throat, and I'll show you in a minute. We know exactly what you've got when you have strep throat. And we know the cause, and we know where it is. It's a very precise designation. When you're told, you have strep throat, that's a very precise thing. However, there are other things that you're told, like depression, which isn't precise at all, as we saw, and some of these disorder designations vary. Look at the changes in the DSM with autism recently. So even what do you mean by a word is a moving target. It's much, much vaguer. The y-axis shows what can we do about it. So there are certain things we understand very well, multi-drug resistant TB, for instance, that we can't do much about, at least not right now. So it's not high up on the y-axis. And when we represent this, we would hope to see that we would have a lot of background data about the nature of this particular disorder, but we would also hope it jumped out that there wasn't much we could do about it. And that's not true now, but that's, I hope, the way we should go, because RDF is so expressive. And if you look up here, as we move up the list, appendicitis, why did you get it? You ask the doctor, oh, it could be lots of things. No one really knows. However, they know what to do with it. So this is something you can do something about it. But on the other hand, we don't know much about it. And that also should be reflected in the definitions. ALS will be down here because, again, we can even genetically say you're prone to ALS, but there's nothing we can do about it. We know the progress of the disease. We know a lot about it, but there's nothing we can do about it. So that's down in this particular area. Now, when you look at SNOMED, which is the go-to scheme right now for disorders and where people want to start building on, you see that it's a mixed bag as to how it represents the state of our knowledge. So here's old strep throat over here on the right, on the left, I should say. I should know my left and my right. And you see it's inflammation morphology, the cause, the site, the process. It's a very precise definition of this particular ailment. We know a lot about it. It's there. Now, we're not designating drugs and other things. We could tie those in. So that could be extra information that we could tie into the particular graph. And pretty much we've got that thing down. And most of the things we've got down, by the way, tend to be much cheaper to both diagnose and deal with, and they often get pushed down to nurse practitioners. So there's actually a financial incentive for us to define things a lot more. But look here. Up here, Goucher's is actually well understood. We can treat it. There are drugs for it. There's, I think, 2 different drugs for it. And we can also do gene tests on it. There, you can actually see the abnormalities, the genetic abnormalities that lead to Goucher's. So we know a lot about it. However, SNOMED doesn't know that. SNOMED basically just tells us it's congenital, it's structure of the nervous system. That's it. So here you have an under definition. You would expect to see many more links in the RDF graph. Now, obviously, we can't automatically find that that's underdefined. We would simply come up with a list of things we would expect a large threshold of links for, and when they don't have that large threshold of links, we can bounce them out and say, hey, you've underdefined this thing. And that would involve a little bit of upfront analysis of what things we understood in a graph like this, and then literally we just do a link check. So this isn't a big rules engine or RF or OWL2 or something like this. It's as simple as graph link checking. Now let's look at something else with a genetic component, Edwards syndrome. If you've had a kid with a woman who's called, what are they called, geriatric mothers, 35 and older, they're usually tested for Edwards and cystic fibrosis and a bunch of other things. And in this particular case, SNOMED is good. It gives the finding site. How would you find out you had Edwards syndrome? It's congenital and the morphology associated with it. So SNOMED gives us information about Edwards syndrome. Unfortunately, Edwards is down here. There's nothing you can do about it. But basically, at least SNOMED is defining what's going on. But contrast that with Overbite. Very simple thing. The United States always dealt with by braces, but other countries maybe not. Again, it's congenital, and there's a morphology. But now, what's the finding site? According to SNOMED, the finding site is, well, you can see it. Look at the teeth. They're bucked. They stick out. And so what SNOMED here is saying is, no, we're not going to chase down the gene path. We're basically just telling you, hey, look in his mouth. Now, of course, for Edwards, you could look at various outward signs and symptoms as well. But because we know where to find it, we can actually go to the specific pathway that leads to it. And yet in SNOMED, they're using the same predicate, the same verb, for both these things. For if you were into old Greek philosophy, the final cause and the initial cause. They're basically using the same verb for both. And that, again, is a bit of predicate or verb fear. In RDF, you generally have no problem making up or coming up with new verbs because you've no problem with sparseness and optionality. And so you would, in an optimal RDF representation, very much distinguish the meaning of these two things. There's clearly a difference between looking at the original genetic cause of something and being able to look in somebody's mouth and see their teeth stick out. And that should be reflected in the model that you have. So here's three different cases. You want it to be much more like this. Here's under definition, and here is overloading of a predicate that really should be broken apart. Again, that will be a hard thing to get at automatically, except, of course, you could find how many times does finding site designate something genetic and how many times does it designate an outward manifestation, a phenotype. And you could then go through the list, bounce out those lists, and actually do some QA that would break down the predicate. Now let's look at something else. This gets into the nature of medical knowledge. You often find there's a lot of stuff you'll read when people say we'll come up with an RDF, an OWL description of all the disorders that are out there, and we'll have everything precise, and we're going to start from scratch. We don't need to use these existing schemes. And of course, I'm saying you should. You start with what you have. And we're going to be pristine about it. But it tends to ignore one big thing about medicine, which is part of medicine is like strep throat. But a whole load of medicine is basically about coming up with a name for a gaggle of symptoms. In some cases, you can do nothing about. And in fact, by definition, you can do nothing about them. And in other cases, certain syndromes that you have no idea why somebody has it, and in fact, it's even named for that. So, you know, not being a doctor, I believe everything on medical shows. And here's a quote from that old show, House MD, idiopathic from the Latin meaning we're idiots because we can't figure it out. Now, what it really gets to is the fact that by definition, if you're told you have essential hypertension, it's hypertension with no known cause. Now, there probably is a cause, and in time, medicine will come up with ways to break down that designation, so the people who used to be given this catch-all designation are now given a much more precise one, and we'll see more precise descriptions. So what we would expect in the system, unlike the Gaucher's example, we would expect to see very few links from essential things. And that again should jump out of the graph, and it does. And so we can gather these together and say, look, this is an aspect of medicine that is much less defined than this other aspect of medicine. And then you get to something which are called functional elements. Yeah, I live in Los Angeles, and I remember somebody told me that very few women in the valley have gallbladders, because by middle age they usually have them out. And one of the leading reasons you get gallbladder out is because you have a thing called irritable bowel syndrome, and if you visit the hospital too often, they say, okay, there's something up with your colon, we have no idea why, but we'll take out your gallbladder. And that happens because the system obviously wants to have something to say. It can't just send you home and say, have no idea, there's no name for it. So there's a number of medical things where literally it's just a name for a gaggle of symptoms. You meet the criteria of a checklist. And in that particular case, we would expect very little extra information in the graph. So what I'm saying is, once we get this into RDF, where links are so obvious, and where we can do basic link counts, and where we can up our game for the likes of Gauchers, for instance, and where we can clearly separate out the functional and the essential from the more understood ailments, we can do a much better job of representing medical knowledge, and we're not representing everything as if it's equally precise or frankly equally valid. So let me scroll all the way back up. I've rambled on a little bit, and I know we've only 15 minutes left. I'm going to hand it back to Eric. What I hope you got out of this was that we're not in pushing RDF for medical knowledge representation, saying, here, come along with our fancy toy. We're actually saying this does something as a medium that the pre-existing media didn't, and actually led people down the wrong path, and that we can do a much better job of representing medical know-how because RDF is such a powerful namespace URL-based medium. Okay, Eric, that's me done.
Wonderful. Thank you so much, Conor. A really fascinating presentation, and I personally appreciate the peppering of humor that you put in there.
Oh, thank you.
We have a couple of questions here. One of them I'm going to modify slightly because I believe that David Booth hit upon what this questioner was really trying to get at. And the question then rephrased is, how does this relate to FHIR? FHIR being the HL7 Fast Healthcare Interoperability Resources.
Okay. Can I have a go at that, David? Do you want to go at it too? I'll have a go, then you can go. Say,
Conor, why don't you start and then toss it over to David, and we'll see if he has anything to add.
Okay. So basically, I'd be mainly talking about medical knowledge representation. And that's terminology, concept schemes, it's called ontologies. There's lots of different words used for it. FHIR doesn't address that. What FHIR does is it references out to concept identifiers. FHIR is basically you could say it's round two of an effort to come up with a format for CCDs and patient records, for portable patient records. The current CCD is far too elaborate for the little it does. And so FHIR pares down a lot of its bad elements and adopts, keeps some of its good elements. So for example, they have a standard description for a prescription, and you need to say, you know, when was it first written, what drug is it for. The drug designation will point into one of these concepts. So you'll either use NDDF or RxNorm or something to designate, or the NDC code to designate the drug. FHIR is agnostic about that. It just says have a drug identifier. And so what I'm talking about is, well, what are the identifiers you should be using within FHIR? And if we normalize down to this hybrid graph of schemes in RDF, FHIR itself will be much more powerful because it will not be using multiple ways of saying the same thing, like multiple ways of saying the same lab test, multiple ways of saying the drug. It'll actually be simpler because you'll always know you're using a particular way. And of course, FHIR can be also represented in RDF and links rather than in plain XML.
Yeah, this is David. So I guess I think you actually just alluded to what I was going to add, was just that FHIR provides a way of expressing or exchanging healthcare data. It's a new standard that's coming up, that's being developed right now, and all of the information in FHIR can be represented in RDF, and any other exchange standard can also be represented in RDF. So RDF is much broader than just FHIR. FHIR is a particular representation for exchanging healthcare data.
Great. Our next question is a bit of a cultural one. So I'll again ask Conor first and then turn to David for his opinion.
Wow, okay.
we're pulling you in here, David. The question is, as medical knowledge workers or semantic web enthusiasts in the healthcare industry, how can we appeal to those who make decisions about what standards get implemented broadly? For example, ICD-10, use in America, being part of meaningful use requirements.
Well, first, let me actually add in one thing on that. Maybe it isn't to exactly this, but it extends the principle a little bit. There's work now with ICD-11, and actually some of that work they're using OWL and RDF and other things. The problem is that the businesses, hospitals in America have had to spend 2-3 years getting up and running with ICD-10. They're not going to take another standard for another 10 years or more because it was so expensive to get up to speed. I think the best way we can get semantic technologies deployed is to show that it is a much more efficient way of using the standards you've already got. You're not going to be able to retrofit a brand new, for example, terminology scheme on top of everybody. And that actually is one of the strengths of RDF. It can unify and bring, as I was trying to talk to, into one graph the best parts of all these different schemes that are actually in active use. And it can enable them fairly seamlessly to start moving off the older ones without necessarily changing their current workflow. And that's one of the beauties of the medium.
And this is David. I'll also point out that when the meaningful use standards are being developed, there is a public call for comment, and anybody can make comments about them. And the people who are in charge of deciding on them are required to take those into consideration. So I would suggest making comments, responding to those requests for comments, and also just contacting members of the ONC, the Office of National Coordinator, to make your views known.
Okay. The next question. I didn't hear which RDF database is being used. Are the performances satisfying compared to other types of DBs, like SQL or NoSQL?
That's a really good question, because actually the DoD interrupt stuff, and David was on this with me as well, that I showed in the middle of the presentation. This gets to an issue of scale. To represent all the medical terminologies, you can literally use Jenna or any of the open source free triple stores, because frankly the number, when it says, oh, it's 1 million concepts, oh, it's 10 million, oh, it's 20 million, those numbers are very easy to handle in off-the-shelf triple stores. And you can do all sorts of complex queries, even though very few of those engines are optimized for complex queries. The issue becomes, it becomes an issue when you are actually storing clinical data about a concrete patient. So for example, you're storing all of the vital measurements, all of the prescriptions of that patient. You're not in the world now of metadata and definitions, you're in the world of concrete clinical data. And now you're talking about trillions of triples. And now you're talking about having to optimize. And there you get pushed into more of the commercial allegrograph space of triple stores. But let me add one other thing, because myself and David worked on this a little bit too. RDF isn't necessarily about a Sparkle triple store. Maybe some people on the call know about JSON-LD. And one of the things we did was we actually represented the patient data. It was RDF, namespaced, but it was actually in JSON-LD. And then we stored the JSON-LD in MongoDB. And MongoDB performed very well, because ultimately patient records are documents. And we gathered all the data there. But when we pulled it back out, because it was JSON-LD, with a simple pipeline, we could get the RDF and put snippets of that into a triple store, even a low-end triple store, and actually do Sparkle queries against it. So once you're in the namespace world, actually it opens up horizons. It doesn't mean you have to stay in Bothanville you can actually go into the commercial things, into the Mongos of the world and the MarkLogics of the world, which actually natively supports RDF now. And you get all the scaling and the support contracts and everything that you want. But you also have all of that definition stuff because of the namespaces to still work on certain subsets within the off-the-shelf databases.
And this is David. I would also comment that just as with any database technology, you have to use it appropriately. You know, if you try to do in relational databases, if you try to do a join across 7 tables, it's just not going to work. You know, it's just the performance isn't going to work. And the same is true of RDF. You know, you have to learn how to do it appropriately, and you have to do it intelligently. But you know, once you take those things into consideration, you know, there is enough performance in the RDF databases to be able to do what we need to do.
Okay. So the next question, that was a good solid question about scalability of database. This next one is kind of the second part of that. It's scalability of workflow, perhaps. It starts with the assumption, I suppose all RDF triples are manually designed and tagged, but how do you deal with millions of concepts then before they can be reduced?
Ah, okay. Well, this gets to that picture I had. Remember, you're talking about the pre-existing. So your starting set, no, it's not manually anything. Actually, if you go to the Caregraf site and look at schemes.caregraf.info, because different terminologies are released on different cycles, the most frequent data we have in there right now, we could do weekly SPRs, we only do monthly. The most frequent data is monthly. It's the first of the month. Of OREX norm and all the drug data. We just have big batches that literally go out to the relevant sites on the right date. They check if the FTP server has been updated. They download the file, and literally the batch job builds the triples, uploads it to a server in Texas, which is what you're doing when you're on the site, and that's what you see. No one manually intervenes in the process of building all of those terminology definitions. Now, obviously, someone wrote the code that imports the CSV file, the XML or whatever, and makes the particular flavor of RDF we use. And that's a maintained thing, and as the source format changes, occasionally this breaks and we have to change the importer. But no, it's not something, otherwise we would be literally dealing with data from 3 years ago because it's such a laborious process. The reason why our data is always up to date is because it's a batched automatic process.
And this, David, I don't think I need to add to that, so next question.
Okay. The technique of using a universal identifier can be extended to multiple language translations, correct?
Yes. Yeah, absolutely. I mean, well, let me add to that, because actually one thing that didn't come out, lexical, famously most of the normalization of data, and UMLS was a great effort in the 90s, was around lexical, was around string matching, was around when you see warfarin, it always means the same thing, when in fact it may mean, it may be just a shorthand for the lab test, and it may not mean the actual compound in the lab test or something like that. So when you do the RDF graphs at their core, it's not so much that they're intrinsically human readable, because you have URI pointing to URI through a predicate, and then we simply annotate labels, and we can attach any number of synonyms for a given concept. So in Scott, for instance, you have a preferred label, and then you can have any number of alternative labels and a more formal thing called a notation. And you can get a lot more elaborate than that. You can start saying, I have a label, and this is actually an acronym. And again, that doesn't change the meaning of the graph. That's simply the human being's entry into it. And those two things are distinct in RDF, where often they get mixed up, I think, in other formats. And
any of those labels can have language, the language associated.
I meant, yes, absolutely, David. It can be French. You can basically annotate that this is a label for this particular language.
Next question.
Well, I'm afraid that is all the time we have for today. So Conor Dowling, David Booth, thank you so very much. This has been a wonderful presentation, and this is only part 2. So to remind everyone, we will be posting the recorded webinar and slides to SemanticWeb.com within 2 business days, so by early next week. And I will send out a follow-up email to let you know the links and any other additional information at that time, so watch your inboxes. Part 3 of this webinar series about the Yosemite Project will take place next Wednesday, November 12th, at the same time. Registration is still open for that webinar, Transformations for Integrating VA Data with FHIR in RDF. That will be with speaker Raphael Richards of the Veterans Health Administration here in the U.S. So you can find more details about that at SemanticWeb.com, and we hope to see you all there next Wednesday. Gentlemen, thanks so much for speaking with us today.
Thank you very much, Eric.
Thanks. Okay, David, bye.
Bye. Thank you.
Bye-bye.